Hi, welcome to our Matlab tutorial. This lesson is on interpolation in a 2D environment. Interpolation essentially is taking known data and trying to find close by data is one way to look at it. You can see there's a pretty ugly equation down at the bottom left, and that's the way that we would typically do it by hand. Well, if we have the data that you see on the right, where there's 4 points, one at 1, one at 2, one at 3, and one at 4. If we know a couple of the points, we're able to find a point somewhere in between. Notice that each of these points are connected by a straight line. This would be known as linear interpolation, where we assume that outside factors between 2 points don't matter, and we're only looking at 2 points at a time, drawing a straight line between them, and then using some fun algebraic expressions to try to find a value somewhere in the middle. Fortunately, with Matlab, we have a built-in function called interp1. And interp1 takes in 4 different variables. So what we're going to find are the interpolated values of a range provided. The first input, though, is x. This is your horizontal coordinates of the data points, or the independent variable. And y is the vertical coordinates, or the dependent variable. The next entry, xi, this is the points that we want to interpolate. If we know the values for when x is 1 and x is 2, but we want to find maybe x is 1.8, we could use different methods to do that. So we could put in 1.8 as our xi value. And the fourth value is method. There's a lot of different methods for interpolation. There's one called nearest. There's one called linear, where we draw straight lines. There's one called spline, or p-chip, or cubic. And these are all methods of identifying an interpolated point between known points. So let's look at an example. We have a function 1.5 to the power of x times cosine of 2x, and we have data for x equals 0 through 5. So this is how we would type it out in Matlab. And if we want to interpolate the entire area, then we simply set the third input, xi, to the same range. And in this case, we decided to use a smaller increment than what x was defined as. That way we get a little bit more granularity, and you'll see a little bit smoother curves in the interpolated plot. So let's look at a few examples. Let's start with linear. So we have the interp1 function. We have x and y as our first 2 inputs. We have the range to interpolate as xi. And then we're going to use the linear method. And notice that the method is surrounded by single apostrophes. So when it's typed into Matlab, you should see that this appears as pink or purple text. We'll also do one for the spline method. We'll call this one yspl. The p-chip method, ypch. And we can also create a function, which is the exact value. The idea behind this is to see just how closely each of the interpolated lines would match the actual equation. So let's look at some plots to compare. So the blue line represents the actual function. The black dashed line represents the interpolated values between points. So let's imagine we wanted to find the value of this function when x equals 1.5. Well, there aren't any points near 1.5. There's a point at 1, there's a point at 2, but you see between 1 and 2, the actual equation dips down quite a bit. If we were to use the linear interpolation, we'd have a value that was pretty far off. Now, near 2.5, you can see it's relatively close, but you usually want to plot to get an idea of which interpolation method makes the most sense for your application. Here's the spline method. You can see it's much closer. The p-chip method, not quite as close. I think the p-chip method typically takes the least amount of area to get from point to point while maintaining smoothness in the curve. MATLAB also has some tools. So instead of hard coding these interpolated lines, you could go into your figure window when a chart gets generated, click on Tools, Basic Fitting, and there are options in there for putting in a specific curve or regression line. Let's look at an example. Let's see if we can actually repeat the same equation. So we have 1.5x times cosine of 2x. So we'll say y is equal to 1.5 to the power of x times cosine of 2x. I think that equation is correct. Yeah. So we will say xi. Actually, why don't we just plot this just how it is? So we'll plot x, y as individual markers. And when we run it, it will want us to save, so we can call it interp example. We get a curve that looks just like this. Now it's pretty difficult to see exactly what's going on with these lines, but if we click on the Tools tab and we go down to Basic Fitting, it sometimes takes just a second to load. And there's all of these types of fit options in here. And all you need to do is click on any one of them, and it will put that line there for you. It will even give you the equation for it. So we have linear, which is just to the order of 1. We have cubic, fourth degree. We also have interpolation, such as spline interpolation, shape preserving, and lots of other options for us to use. Now, it is important that we understand how to hard code these types of curve fits and interpolated values, but as long as you know that all of the figure editors have the same options to go into Tools, Basic Fitting, and select your curve.